Hello guys, so today we are going to practice the May 2024 version of Unit 3 Edexcel Physics. So let's start right away. Okay, so let's look at the first question. A student investigated the force needed to break a rubber band. He planned to use the apparatus shown. The student suggested pulling down on the force meter until the rubber band breaks. Identify two health and safety issues and how they should be dealt with. Okay, so guys, whenever you start solving a paper, the first thing you need to read the questions very carefully. This goes without saying. Many students make mistakes understanding the questions. So read the question very carefully, look at the marks, and then start answering the question. So we have to think about two health and safety issues. So we've got a rubber band and there's a force meter attached to it. What the student is doing is they are just trying to see what force would be needed to break the rubber band. Um, this is an easy question. We know that if you hang something very heavy from a rubber band, the rubber band, there's a chance that it will break, and we are actually over here trying to investigate at what force will it break. So when it will break, what will happen? When it will snap, it might hurt the eyes of the student. So we can say that the rubber band might snap and hurt the student's face or eyes. They asked us about two health and safety issues and how they should be dealt with. So, how can you deal with like there are many experiments in which it's dangerous for your eyes. Something is dangerous for your eyes, like if you're working with lasers, if you're working with rubber band. So you can say that just wear safety goggles. So wear safety goggles. Okay, so now the second issue, health and safety issue, that could be there's a stand here, there's a force meter. When the rubber band will break, the and when you are actually increasing the force by using the force meter, the stand might fall down, it might imbalance, and it can hurt the student's feet, it can fall down. So we can say the stand might fall down and hurt the student's feet. And how can we prevent that? We can fix the stand. Like we can put something heavy over here on its base so that the stand remains vertical. So fix the base of the stand by placing something heavy on it. So that's about the first question. All right, let's move on to the next question. Describe a method the student could use which would not include a force meter. You should include the use of additional apparatus. 2 marks. So, this is again an easy question. If you don't use a force meter, what you can do is you can just attach masses to the rubber band. Okay, you can put a hanger with the hook. In the hanger, you can attach masses. Those masses, when they're pulled down by the because of gravity, they'll be pulled down. The rubber band will extend, and at a certain value of weight of masses, the rubber band will snap, and you can measure that weight. Like you already know how many masses are there, so you can measure that weight. So what we can do, we can attach a hanger to the rubber band in which we can place slotted masses. So we can increase the masses, increase the mass until for a certain value of weight, the rubber band snaps. So that value is the force. So weight over here would represent the force. So yeah, this is the alternative. Okay, next question. The student investigated how the breaking force of the rubber bands changed at low temperature. The student placed 5 identical rubber bands in a freezer at -10 degrees C. The student removed one rubber band from the freezer and determined the breaking force. He repeated this for the other rubber bands. Explain why it is appropriate to repeat the measurements. Okay, so what's happening here? Uh, the student measured the breaking force for all the other rubber bands. What he's trying to do is he's trying to investigate how the breaking force relates to low temperature of the rubber bands. So instead of just choosing one rubber band, he used 5 identical rubber bands. Now how does that help you? So for so if the student just used 1 or 2 rubber bands, there could be a problem with one of the rubber bands, okay? Because when you're doing an experiment, there can be all sorts of problems. It could be the way, it could be like something the student does, some mistake in the experiment that can affect the data. So by taking 5 identical rubber bands and then measuring the force for those, the breaking force for those, for all of them, if there's any anomaly, the student can easily detect it. So because the rest of the rubber bands, they'll just show pattern. It'll be closer to one value, but for the anomalous rubber band or for the rubber band uh, during the experiment of which there was a problem, the student would easily be able to detect that. So we can say that this is appropriate to repeat the measurements to discard any anomalous data that arises because of a fault with one of the rubber bands. Um, or due to or because of how the student handles it. So because of this, by doing this, the student can be sure if there has been some problem in the experiment or not. So they are essentially discarding any random errors in the system, detecting and uh, discarding that. So in short, we can just say that this is a longer version of the answer. We can just say that it will reduce the random error in the system. And that random error could be like if there is a slight difference in temperature, because remember, we are investigating the effect of temperature on breaking force. So if there is a slight difference in temperature, that would affect the breaking force. So we can just say that it is appropriate to repeat the measurements to reduce random error due to a slight difference in temperatures. And actually, what we can do, we can just replace the fault thing over here with just the temperature. So because of slight difference in temperatures of rubber bands. Um, okay, so yeah, this is how we can answer. All right, let's move on to question 2. So question 2 is about a student investigating a ball bouncing from a slope using the apparatus shown. The student used a protractor to measure the angle theta of the slope to the horizontal. She dropped the ball from the initial position shown. She used a meter rule to measure the distance x. She varied theta and measured corresponding values of x. State one control variable for this investigation. Okay, so what's happening here? The student is trying to find out that how the angle of the slope affects the distance of the ball between the initial position and the landing position. So if you change this angle, how will that affect how far off the ball lands? So theta is the independent variable, the angle is the independent variable, and the distance is the dependent variable. So they're asking about one control variable, something that will keep constant during the entire experiment. If we change that, it will affect our values. So a very obvious one is that the height of the ball. Because if we drop the same ball from different heights every time, what will happen? The the gravitational potential energy of the ball will change. So let's say if I drop the ball from here and I just like it has a gravitational potential energy of mgh. So when I changed the gravitational potential energy, let's say I increase the height, what will happen when the ball will fall down, all of this gravitational potential energy, some of it, uh, most of it will be converted to kinetic energy. Because when it falls down here, um, it still has some gravitational potential energy because it's not on the ground. So when it'll be converted into kinetic energy, so we will have like, you know, this and the velocity would be dependent on the value of gravitational potential energy. So if we change the height during the experiment, it will change the velocity with which the ball jumps, and therefore it will change the distance. So we need to be careful with that. So we can just say the height of the ball. Um, yeah, initial height of the ball. Explain why it is necessary to control this variable. So the same thing that we just discussed, so if the height is changed, the gravitational potential energy of the ball changes. And therefore the kinetic energy of the ball when it hits the slope uh, this affects the velocity, which in turn changes the distance. X. Now, you might think that my answers are a bit longer than yours. That's obviously personal. Everybody writes differently, thinks differently. But what I always make sure and what I tell my students is you have to make sure that your answer is linked. Okay? The argument should follow smoothly. There shouldn't be any missing links. If somebody reads it, they are able to follow easily what you're trying to say. They shouldn't have to guess some missing points. Okay? So you have to make sure that everything the examiner wants is written there. So, okay, moving on to part B. The student recorded the following data to plot a graph of theta against x. Criticize the recording of the data. So, when you look at this data, what's the problem? So this one's easy. Um, so first of all, if you just see there are just three readings. Now, whenever you do an experiment, you always make sure to at least take 5 readings, even more, because the more values you take, the better, the more accurate your experiment is. So, so we can say very few values of theta and x, like there should be more. What else? Now, if you look at x, we can see that this point over here. So we have 35.8 centimeters, 61 centimeters, and 592 centimeters. How can that possibly be? So that's an anomaly. So 592 centimeters is an anomaly. Um, Apart from that, what else? Uh, the values of theta, they have been, there's not like, it's close, but it's not like a uniform gap between them. Significant figures is also a problem. So inconsistent significant figures. Yeah. Um, yeah. Okay. Another point, like we just need 3 points over here. It's just a 3 marks question. But if you had to write more, you can always include it for this kind of data. So they haven't repeated any values. So for example, they measure the angle and it's 10 degrees and they just stick to that. In an ideal experiment, you should repeat it because maybe the angle is 10.1 or 10.2 degrees. So you should always repeat it. So the values of angles and the values of x, they were not repeated. They were just recorded once. That's a problem. Okay, moving on to the next part. The student wrote a laboratory report about her investigation. She reported that the most significant source of error was being unable to judge the exact point where the ball landed. This was because the ball moved too quickly. Explain one modification she could make to the apparatus to reduce this error. You should include additional apparatus. Hmm. So in this question, we have to point out how can we make sure that the ball lands? How can we make sure where the ball lands? Because the ball is moving too quickly, so it can be a bit difficult to judge, very difficult to judge actually. So how can we reduce that? So the easiest way to do this, like in any such question where you are recording some movement and with the naked eye you can't just record it precisely or accurately. In all such situations, what you can do is you can just use a video camera, okay, that captures in slow that captures the movement, and then later on in slow motion you can watch it and figure out where the ball exactly landed. So this goes for all related questions where it's difficult to observe. So use a video camera to record the motion of the ball. So the video camera must be placed in such a way that you're able to see where it lands on the slope. Record the motion of the ball. You can watch the video in slow motion. Figure out where it landed. That's one way to do it. Okay, moving on to question 3. All right, so it says a student determined the speed of ultrasound in air using the apparatus shown. We've got an ultrasonic transducer which just emits ultrasound waves. There's this tube, a transparent tube in which there's water and there's air. Over here, the length of the air column is S, and there's a wooden block on top of which all of this is placed. So the transducer will emit sound waves. They said that we are doing this experiment to measure the speed of ultrasound. So it will emit sound waves. The sound waves, when they'll strike water, they'll reflect. Some of them will reflect. When they'll reflect back, they'll go here. So if we measure this distance, and we also measure the time taken for the pulses to go to the water boundary and reflect back, we can then find the speed using those values. So part A is about the student added water to the transparent tube to change the length S of the air column. Describe a method to determine a single value of S as accurately as possible using a meter rule. Your method may include additional apparatus. So, what's the question about? We have to measure the length S as accurately as possible using a meter rule. How can we do that? So, any such question, this is a very common type of question you get in Unit 3. Any such question where the meter rule is where you need to use a meter rule to measure a length, and especially if it's like the length is vertical. So, first of all, you have to make sure that your meter rule is placed exactly where it needs to be. So in this case, that would be like it should be aligned with the bottom of this air column. Because if it's not aligned there perfectly, like you think it's aligned, but it's not aligned there perfectly, well, you'll take an anomalous reading. So the base of the ruler should be aligned with the water level. Then, whenever taking vertical readings with a meter rule, the meter rule must always be vertical, like exactly vertical. Because if it's not vertical, if it's slightly tilted, you'll get a wrong reading. So ensure that the meter rule is vertical. And how can you ensure that? You can ensure that by using a set square. Uh, yeah, so by using a set square, you can ensure that it's a 3 marks question, so that's why we are aiming for 3 points. The third point, again, where a very common point that you can mention in such type of questions. Whenever you're taking a reading using a meter rule, you have to take the reading perpendicularly from the point. So over here, you need to take the reading at this point, right? So you have to view this point. If I show it by a different color, so this red area, you have to view it perpendicularly. Because if you look at it a bit from up or a bit from down, you'll record a wrong reading because of parallax error. What is parallax error? This error occurs because you're looking at things in a certain angle, so they don't appear to be where they actually are. So, the third point is take the reading perpendicularly from the uh, from the tip of the transducer. So, okay, so take the reading perpendicularly, like from the meter rule. Yeah, okay. So yeah, these 3 points are necessary over here. All right, moving on to part B. The ultrasonic transducer emitted pulses of ultrasound. The emitted pulses were reflected at the water surface and then detected when they returned to the ultrasonic transducer. The student connected an oscilloscope to the transducer to determine the time between an emitted pulse and the reflected pulse. The oscilloscope screen is shown below. Horizontal axis represents time. The time scale was set to 0.5 milliseconds per division. Show that for this example, the speed V of ultrasound in air was about 330 meters per second. Length of air column is 49.7 centimeters. Okay, so this question talks about an oscilloscope. What is an oscilloscope? It's a device that just shows the waveform of any input signal that you give to it. So over here, the input signals here are the emitted pulse. So the sound wave that the transducer first generates, that and when it travels into the air column, reflects from water boundary, comes back. So the reflected pulse. These two are input signals that the oscilloscope screen shows. Now the oscilloscope screen is always shown in these boxes. Um, on the horizontal axis, it represents time. Now the time was set to 0.5 ms per division. In all your physics exams, it's very important to look at the units. So sometimes students mistake units, like they don't see it carefully, or they might read it wrong. So this is milliseconds, that is 10 to the power minus 3 seconds. So times 10 to the power minus 3 seconds. So we have to find the speed of the ultrasound. So what would be the speed equal to? Speed would be equal to the distance that it traveled over the time, right? Now we know the length of air column is 49.7 centimeters, but the uh the ultrasonic pulse, it traveled twice that distance because it went in and came back, right? It went in and returned. So it traveled twice that distance. So the distance over here is not just 49.7, but 49.7 times 2. And since we need to find the speed in meters per second, we will convert this to meters, centimeters to meters. So 49.7 over 100. So that is 0.497 meters. So our distance is actually 2 times 0.497. And now let's find out the time. We know the time is on the horizontal axis. This is time. They said each division is 0.5 milliseconds. So let's count the divisions. So we can do that from the peaks. So 1, 2, 3, 4, 5, and 6. There are 6 boxes between the peaks. Okay. So this means the total time would be 6 times 0.5 milliseconds because each box, when they say division, like this is one division, like it's the width of one box. So each box is 0.5 milliseconds. So 6 boxes would be 6 times 0.5 times 10 to the power minus. Now let's calculate that. So we get 331.3 meters per second, which is very close to 330 meters per second. So our answer is correct. Okay, moving on to part C. Um, okay, the student varied S and determined corresponding values for V. He recorded the following values. There are 4 values for speed that he recorded. Determine the mean value of V. Now, everybody knows finding how to find the mean value. So mean is just equal to the sum of values divided by the number of values. So that would be 335 plus 347 plus 339 plus 342 divided by 4 because there are 4 values. Now let's find the answer. Okay, so this gives us 340.75. But remember to take into consideration significant figures. Always remember, you should never forget these figures. Significant figures are actually significant. So for your marks, they're very significant. So you are getting an answer of 340.75. So your data includes 3 significant figures. All of them have 3. If like didn't have the same number of significant figures, then your final answer should have the least number of significant figures. So let's say if there was a value that looked like, for example, that just had like 2 significant figures, then your final answer should have only 2 significant figures. So this would be, you'll round it off, so it would be 341 meters per second. Next question, determine the percentage uncertainty in the mean value of V. Percentage uncertainty. Now, what is percentage uncertainty? Percentage uncertainty, it's always equal to the absolute uncertainty over mean value times 100%. That's like the general formula of percentage uncertainty. So, mean value, you've already found that. How do you find out the absolute uncertainty? Now, that depends. Uh, Sometimes absolute uncertainty is just this kind of number, like, and let's say you are told that there's a reading which was 3.0 plus 0.2 plus minus 0.2 centimeters. For example, if you are given a data in this form, then this is the absolute uncertainty. Okay, the number written next to plus minus. But if you're not given data in that form, like you're given a data in this tabular form where there are several values, then the absolute uncertainty equals range divided by 2. You find the range of values and divide by that by 2. If you don't know what range is just highest value minus lowest value in the data. So you substitute that here and you get the final answer. Um, Sometimes, now there's a third case too, where it's neither presented in tabular form nor is it written in this form. What do you do in that case? Well, you can, like, for example, they talk about an instrument, like, for example, a meter rule, and they ask you to find its percentage uncertainty. You know the mean value, but how do you find the absolute uncertainty? So a meter rule is an analog device. So it's the lowest value that you can measure is 1 centimeter. So its absolute uncertainty would be 1 divided by 2. You will just, whatever uh, the lowest value is, you will divide it by 2. So that is 0.5. So in that case, your absolute uncertainty would be 0.5. So there are three cases. Uh, you need to be careful with that. You should know all three to be able to face all these challenges in the exam. So let's find out the absolute uncertainty for this question. We have highest value over here is 347. Lowest value is 335. That is 12. So we are doing 347 minus 335 over 2. That gives you 6. Okay. So 6 is your absolute uncertainty. So let's calculate that. 6 divided by the mean value, which is 341 times 100. So we get 1.75%. That is the percentage uncertainty. Now, I'd request you to write neatly in the exam. I'm just explaining, so I've annotated everywhere, but please be write neatly when you write in the exam. Okay, the last part of this question, the student modified the apparatus to determine the speed of sound in water. He determined the speed of sound in water to be 1,444 meters per second with a 4% uncertainty. The accepted value for the speed of sound is 1481 meters per second. Deduce whether the student's value for the speed of sound in water is consistent with the accepted value. Your answer should include a calculation. Again, a common type of question for Unit 3. So you have a measured value with some uncertainty that's given to you, and you're provided with the accepted value. You have to say that is this value that you found uh consistent? Like, is that accurate with this like experimental value? So what you'll do, you'll just find out this uncertainty. This is fractional, sorry, percentage uncertainty. You will change it to absolute uncertainty, add and subtract it to 1444, and find out whether 1481 is in that range or not. So let's do that. So 4% of 1444 is just 4 over 100. Percent is divided by 100 times 1444. So let's see what we get. So this is 57.76. So this means that the value the student recorded is 1444 plus minus 57.76, right? So let's subtract that. So 1444 minus 57.76. So this means that it is from 1386.24 to 1501.76. So this is the lowest value. I got this when I subtracted 57.76 from this 1444. And I got 1501.76 when I added these two. Okay. So this is the range of values the student gets. And what's the accepted value is 1481. Does it lie in this range? Yes, it does. So the student's value is consistent. So 1481 meters per second lies in this range. So the student's value is consistent. So yeah, that is how you solve this question. Um, okay, so I hope you liked this video and we'll cover the last question in the next video. Do check that out. So see you guys. Have a great day. Happy learning.